do is put that context out, put everything up there on the left side of the board, and then we'll start working with the thing. So the idea was to put everything up here. So we've got some irregularly shaped mass distribution. X1, X2, X3 axes at the located coordinate center of mass. Those are going to be the primed axes. No. Good. And then we're out here somewhere at a great distance. There's the point R. This would be a vector R prime for a point mass. And so the distance from there for the vector is R minus R prime. The distance is its magnitude. And so instead of just having one point mass, we had to do a whole integration. Our potential is minus G integral dm prime. So it's just all the point masses at R prime over this distance here. So that's what we had to do. And what we did was then a Taylor expansion. We did a Taylor expansion of this form here. Or one, by the way, if you have nothing better to do someday, just to try to reproduce that calculation we did, x I prime, xj prime. So that was the general thing. We ended up with the following. V of R is equal to minus G total mass over R minus G 1/2 double sum ij qij, and then we had xi xj over R to the 5th. So there were a few interesting steps taken between here and here, but this is the object we now have to get a grasp over. And the first thing we see is ordinate center of mass to 0th order, or to this 1 over R. It just acts as a point mass at the origin. Okay. And so these are the correction terms. And so one of the things we're going to work on is if there's a spherical, if you have a spherically symmetric mass distribution, these next terms all have to vanish identically. And we'll actually take that as a proof of this important point mass property. We're going to prove it in a couple different ways. So yeah, let's write down what these Qij, it's called the quadrupole tensor, and integral, I'll just put it this way, dm prime 3xi xj. I'm going to put them primed in this description here because it means we're integrating over the body. When we actually do the integrations, we don't have to have any kind of prime, right? We know what we're working on. And you're going to end up with constants. So it's a 3x3 matrix, and it has these important properties. First of all, that the sum of the diagonal elements vanishes. We looked at that last time. That's pretty basic. But also, if the body's symmetric, the off diagonals vanish. So this thing turns into a very basic calculation. There's no problem. Let's put it this way, unproblematic calculation. That's as far as we had gotten last time. We just got to look at this a bit more now. One of the homework problems was going to show that these things vanish if you have a spherical symmetry. So I'm just going to set that up right now because it's the kind of thing we can do very explicitly, or we can actually just investigate it and consider that a proof. So we're kind of going to do both. Okay. So that's what we're going to do next. So suppose, I'll just write here so we have some terminology on the board. Quadrupole tensor. 3x3 symmetric matrix. Right, so Qij equals Qji on inspection and so forth. So here's our calculation for spherical symmetry. Spherical symmetry, we have dm is equal to rho of r, and then we can have, so rho d volume will be r squared dr, no, I'm sorry, r squared sine theta dr theta dθ, right, if we go to spherical polar coordinates. I think this is pretty much the last thing we had on the board last time, right? So let's just look at Q11, and we'll see this will be very general. Q11. So now we have our rho of r squared sine theta dr d theta dθ, and we won't write it down. We'll just state it. The dr goes actually from 0 to infinity, whatever you have. The d theta is 0 to pi. The d phi is 0 to 2 pi. Right? Those integrations. But yeah, now what we want to do is fill in what this is. It's 1, 1, right? So it's 3x1 squared, 3x1 squared minus, and then what's that r prime squared? x1, and we're not priming, okay, so 3x minus x1 squared plus x2 squared plus x3 squared. I'm claiming by inspection, because we haven't translated this into plain polar coordinates yet, but we'll just go underneath here. And what we have here is 3x squared minus x1 squared, so we have 2x1 squared minus x2 squared minus x3 squared. I'm claiming we can just declare victory here if we inspect this carefully. In other words, all right, here you go. Spherical body, spherically symmetric, spherical body. And this is an important skill. If this integral really is just 0, we save ourselves a lot of work to recognize that it vanishes. So we'll look at the blue expression here. Let's put it down. Let's see if we can come up with an argument why this integral will vanish. Spherical symmetry. Now, of course, if we want to plug things in, I'm tempted for us to do both. If we want to plug things in, we have to have, x1 equals r sine theta cos phi, x2 equals r sine theta sine phi, x3 equals r cos theta, right? Spherical polar coordinates. Okay. So why would that integral vanish? Anybody? Spherical symmetry. So we're literally integrating over a sphere. So here's our sphere, these are our x1, x2, x3 axes. Integral's gonna equal 0. Probably gonna have us do it just to, crank out a little spherical polar coordinate stuff. But, just be sines and cosines. So anybody get the symmetry argument? It's a sphere. So these integrals, it's on the tip of my tongue. So x1 squared and x2 squared and x3 squared have the same property out from 0 to r, right? They're just right. It's true. So whether I go in this direction or that direction or the third direction, the integral itself has to be the same. So if I go out in that direction twice with x1 squared, it's the same as if I subtract off the x2 squared and x3 squared integral. Make sense? Yeah. So that proves that that's equal to 0. We can just check it off and get on with our life. What's the important one? You know what? For the homework, though, and this won't take you long. For the homework, go ahead and plug all these in. You'll square and sum and simplify, and you'll end up with a couple of sine squared type of, sine cube type of integrals. You can do them all, okay? So for the homework, plug in, take star into the integral and evaluate. But yeah, so now we've, we'll have, for a couple of reasons, we're going to add a third reason to this whole thing later, that these contributions vanish for a spherically symmetric object, and then you're just left with this. And that's so important if you are orbiting Earth and you're only this far away, you've got the spherical symmetry, and therefore it's as though you're orbiting the center of Earth, and your distance is measured here. So you have that simple potential. Although for the Earth, you don't have the perfect sphere, and then you actually do get some of these contributions. That's our next task, is to tease those out as well. Good. So that was the one homework problem, and you really want to just set it up, make it clear to yourself. You can even state this argument first, but then knock out these integrals. You guys remember doing spherical polar coordinates at all? So you're going to end up, what you're going to end up with is your rho of r and your r squared and your r to the fourth. That separates, the dr, and then you'll have your d phi 0 to 2 pi. They all separate nicely. There's nothing, and you'll have your d theta 0 to pi as you can create them. So it'll be no problem. Okay, good. So we have this. I'm going to leave all these on the board so we can keep looking at them. And then we'll look next at the simple massive rod about the x-axis. So that's where we're actually going to dig in here and see how these things work and how they look. X and Y, so now we have X1 and X2, X3 is coming out of the board, and we have that massive rod from minus L over 2 to plus L over 2. And I don't know the answer exactly, but remember we had calculated V of X with that logarithm, we expanded the logarithm, we got those 1 over we had found minus G dm over x plus some terms, but then we had also done b of y minus gm over y plus some correction terms. So we had those two integrals. This time we want the quadrupole tensor for this map, this rod here. So this is forward work. I'll just write here previous work. We want to reconcile the results is what we're going to do. So here, I may have to free up the left side of the boat after all. What we want is Q11. We already know that we're going to have this form. So we'll have this integral minus L over 2 to L over 2, and the dm is the m over L dx1. Okay. Now in here, roughly what I had there a minute ago, 3x1 squared minus x1 squared plus x2 squared, x3 squared. So before we calculate, we have to think about this a bit. So I'll leave this here. N over L dx1. And we have the same thing. 3 minus 1, we have 2x1 squared minus x2 squared minus x3 squared. Now, because this is just a thin rod, it has no dimensions in x2 and x3, right? We're idealizing it as just a linear rod. So for that reason, these two are identically 0. It has no extent in those directions. Remember, we're integrating over the body here. I just dropped the primes because we don't need any more. Yeah, so this one is quickly done, right? In fact, I'll just use this corner up here. So this Q11, we've done things like this before. We've got the M over L. Apparently we have a 2, and this is going to be an x1 cubed over 3. So it's going to have a 1/3, and that odd function is going to give us another 2 times, and then it'll be L over 2 cubed. So that's what actually comes out right there. And we have ml squared, and we just have to deal with the coefficients there. We've got 4 in the numerator and 24 in the denominator, so over 6. Okay, so we're going to fill that in. I'm just going to need some more board space anyways. So yeah, make sure you do that calculation and catch any errors. Because the argument now is, this is all we had to do for an integration. Because, do I have enough on the board here? Yeah, Q11, that's this integral along this x1 axis. Whether I look at this thing from the x2 axis or the x3 axis, it looks the same, right? If I'm up here at x2, I'm looking down at a bar. And if I'm in the x3 axis, I'm looking down at a bar as well. So So Q22 and 33 are going to be equal to each other. And the sum of the three equals 0. So you could say we're essentially done. We have Q11 plus 2 times Q22 by that argument, right, is equal to 0 because they're both equal. So Q22 is equal to minus Q11 divided by 2. And so that's minus ml squared over 12. And same with Q, so 3. So we have to, then we're gonna have to go into this expression and see if it all makes sense. So now we have for that bar there, Qij equals m L squared over 6, 0, 0, 0, minus ml squared over 12 over 12. That's a 3 by 3 matrix. It has nothing but diagonal elements, and they all add up to 0. And for for symmetric bodies, you're always going to have this feature. You may not have all 3 of them, or you may not have 2 of the 3 being equal to each other, but they'll add up to 0. You have to do then most 2 integrals. Okay, so what we want to do now is expand this out and see what it looks like, and then the proof or the goal is to reconcile this to our other calculations. Anybody have those other calculations on them? Remember we had them on the homework, those the expansion, when we had that logarithm, we expanded it to the second and third order. Maybe. Don't have all those belts memorized, but anyway, if they don't come out the same, we're gonna have to go back and find our mistake, right? So here, what we're gonna do next is we're going to expand this thing out very explicitly, and then look at the relevant limiting cases. And I have a couple of other things up my sleeve. This is getting hard to clean. Okay, so let's write this out very carefully. So for this example, this picture I just erased, what we're going to say is we have b of x1, x2, and x3. That's our b of r. The first one is simply minus g total mass over root x1 squared, x3 squared. So that one I'm going to write out explicitly. Now the other one, minus g, go ahead and put the 2 here. So we've got this double sum, okay? But since it's only a diagonal matrix, what we have is Q11, I write that out somewhere, I'll put it underneath. We've got the Q11 times this, and the Q22 and Q23. So we have G ml squared over 6, and I'm going to write x1 squared over r to the 5th. I'm looking at write that back there. X1 squared over the 5th. Then we have minus ml squared over 12 x2 squared over r to the 5th minus ml squared over 12 x3 squared over r to the 5th. And then there would be more, but we're not interested in those. That's the explicit expression here, and this of course is Q11 x1 squared over r to the 5th, etc., right? So this is very general, but what if now one we did on our homework, or in class, or both, okay? So we can say b of x1, so we're simply along the x1 axis. Then the first one there is minus gm over x1. And what's the second expression going to be? The x2s and 3s are gone altogether, so we're just looking at this one here. We end up with minus gm over 2 times 6 is 12. And we have x1 squared here, we're going to have x1 to the 5th, so gm L squared x1 to the 3rd. And that's what I was saying we want to compare with. Okay, we want to compare with, because we had done that Taylor expansion of the exact result, you know, purely along the x-axis. So this should just come out, and it's somewhere in our notes or our stack of work. And same thing for v of x2 that we had done. We just by inspection of this thing, we'll have the minus gm over x2. Now we have a minus times minus is plus gm L squared over 24 x2 cubed. So we had to go compare, okay? Somewhere in our results, they should match. They should match and reconcile. And these are those corrections. And as advertised at the very beginning of all these exercises, it's that 1 over r cubed or 1 over distance cubed as the next correction. This is just the point mass expression, and this is based on the mass distribution. So anyway, this also is homework, so if you just take these and put them all together and recognize what's going on, you'll be in good shape. This, by the way, is a lot less work than what we did before, right? When we had to expand that logarithm out to the 3rd order. So I want to do one more thing with this. I think we have time. And but this is the general form of what we're going to see. We want to get the quadrupole tensor for a ring of mass or for a disk of mass. Because a disk is the extreme case, you know, of a flattened sphere. And that one will make some good connections as well. Okay, good. And what we're aiming for, of course, remember the absolute angle and the beta over r cubed term, right? That's what we're aiming for, because that was actual front. So this is preparation for all that. This time we're doing the quadrupole tensor. We'll do it of a ring. That's a ring, a massive ring. Maybe I could assign the disk as a homework. Speaking of homework, since we didn't talk about that this week, the exam rewrite would be due Friday, and then these 2 problems that I just did, we'll put those on as well.
For Friday?
For Friday, yeah, for this Friday. And I don't know if anybody had any questions. Did we talk about the exam very much the day I handed it back? I think so.
I think the week before we went on.
Exactly, yeah. Week before. Been a while, but any questions come up, you know, we can talk about that on Friday too. So yeah, we've got time. Let's do this ring, and that's going to take us back to our astronomical calculation and its whole motivation. The actual ellipsoid, I think we'll save for next semester. We've got to get some integration skills for that one. Okay, so our next thing is the quadrupole tensor ring. So, ring, and I'll just say it, ring, mass M, radius R. So that looks like this. And in fact, this picture we want to make big, do a little more with it. So we've got the x1, x2, x3 axes, and we're going to put the ring right here. You know, radius R. So in this case, I'll just put this here. We've got enough symmetry, we definitely have this. Two of these three are going to be the same. Which ones?
Q1, Q2, right?
That's right. Q11 and Q22 will be the same. And we've got that symmetry, and then the Q33 will be different. So we know that much. So we can do Q11 again. And we start with the, DM 3. In fact, we've done this a couple times. We can say 2x1 squared minus x2 squared minus x3 squared. If you don't mind. And in this case, the x3 squared is the one that's going to vanish because we have no extent in the x3 direction. And we can even say the x1 squared integral and the x2 squared integrals are going to be the same, right? So for that reason, we can say good, that'll be dm x1 squared. And we're integrating over the ring. So since it's a ring, we'll do this. We'll do mass of the ring over its length, which is 2 pi r. So that's the linear mass density. And then we'll have r d phi, which will be the, the length element. We'll have r d phi. So this will be 0 to 2 pi. And our x1 squared, we can say is r cos phi squared. So these integrals kind of make up as you go along, right? It's best to use this dm formalism and then decide on what you need as you go through. So this was good. And we've got m over 2 pi radius. We've got another radius here, and another 2, as actually has to be. And then we'll have the integral of cosine squared phi d phi from 0 to 2 pi, which will just be pi. And so pi will cancel, as does one of these. R stops the bottom. So we end up with mr squared over 2. So we have mr squared over 2. Remember, we agreed that Q22 is going to be the same. So this one will also be mr squared over 2. And this last one,
Negative mr squared.
thank you, negative mr squared. Good. That's the quadrupole tensor for the ring. And the last thing we want to do with this is set up the general expression This will bring something new into play. See if I can pull that off. Okay. So what we want to write is V of R. Let's put it this way. And we know we already have minus GM over R. And you know, this time I'm going to add to this picture here. Yeah, here somewhere at point R. And I'm going to add this angle theta, which hasn't played a role yet. Okay, the integration we just did was phi in that x2 plane. Then we have minus G, and we have that 1/2, got the double sum, ij 1 to 3, etc. I'm gonna write this one out again. Minus G over 2. Q11 over R5 plus 2, 3, 3 x 3 squared over R5. Squared over 2. Okay, so we've got mr squared over 2. And if we do that, we have x1 squared plus x2 squared plus what? 2x3 squared. Oh, minus x3 squared. Okay. And then we have, I'll put the r to the 5th right here. R to the 5th, keep that away for a moment. Now this can be manipulated, and I'll just do this right underneath. I can say this is x1 squared plus x2 squared plus x3 squared minus 3x3 squared. And if I do that, and now go back to my my spherical polar coordinates, this here, I can take an r squared, right? x1 squared minus 3r squared cosine squared theta. Because the meaning of the x3, right, r cos theta. So this gives us a new useful expression. We go up here with this equals minus gm over r. You've always got this one at the front. Minus gm r squared. I'll just write over 4 r to the 5th. And you see I've got that r squared minus 3r squared cosine squared theta. So I can actually factor out the r squared and have r cubed and 1 minus 3 cosine squared theta. And this is going to be one of the first of the special functions of the multipole expansion in theta and phi that goes out to infinity. Okay? So then you've seen this before as a first term of the multipole expansion. So we've made contact with that, and what we've especially made contact with, I forget even, I was the Legendre polynomials, one of those special functions, okay? So what we've especially made contact with is this, minus gm over r. Okay. Now we've got, I'm gonna do this, minus gm r squared over 4, you know, 1 minus 3 cosine squared theta, 1 over r cubed. Okay. And suppose theta is equal to pi over 2. Theta is equal to pi over 2, that means you're just in the plane of, say, the orbit of a central spherical body. And then this would be our, you know, alpha over r, beta over r cubed, right? And so remember that beta over, let me clean this up. I got perfect time. Okay, so I'm gonna erase this. You see, I did a couple of steps, got up to here, down to here. And now I just need some room here to finish this off. So now I have V of R, so M times V of R is U of R, as when we were doing our astronomical absolute angles, right? So we could have, got room right here, so U of R equals minus G M F over R minus G M R squared over 4, 1 minus 3 cos theta, bracket 1 over R cubed. Now for us, this is a ring. For a disk, I'll have different numbers here. For a sphere, I'll have different, or for a spheroid, I'll have slightly different numbers here. But this is the form that we have, right? Remember we had U of R equals minus alpha over R plus beta over R cubed. So that beta we were talking about, we were doing the absolute angle, so it's actually related to the mass distribution. And of course, we're not orbiting a ring, but like I said, a disk is going to just have a different factor instead of here for the 1/4. And the same thing actually for a spheroid, okay? For an oblate spheroid. And yeah, the idea here is for, you know, for theta equals pi over 2 plane of the orbit. So you can work the other direction as well. If you're carefully analyzing this thing from orbital data, right, then you can make a conclusion as, you know, you can start to use that as in your analysis of the mass distribution. That's the point, okay? So yeah, so the astronomers have all kinds of stuff at their disposal. They make really meticulous and accurate data, and then they can start to know what the structure is of the thing that's being ordered by that. Because this is mass distribution information. Anyway, that's as far as we're going to go today. But that's what we were headed for the whole time when we did this. You know, at the time when we did absolute angle, I just pulled this out of that. Right, but now we've actually justified everything. Next semester, I think because we're going to do integration for rigid body motion. Then we'll go ahead and do the actual oblate spheroid here. But it won't give us anything, it'll give us, you know, a concrete result, but it'll be the same thing that we got right there, fundamentally. Good, there you have it. That's all I've got for you.